to you. Okay. So I hope you can see the slides, and hopefully when it transitions later, you'll be able to still see it. So we are on phase equilibria, and this is linked to the slide on multi-stage processes, which will talk about stage-wise operation. Okay, let me know if it will not transition as I go along. So when we speak of phase equilibria, so this has something to do whenever a particular condition is reached already, wherein any form of transfer, specifically in the case of unit operations, mass transfer ceases or stops. So mass transfer ceases when an equilibrium between the two phases is reached. So it doesn't mean that there isn't any movement at all. It's just that the rates of the movements in the forward and in the reverse directions are said to be the same. And as such, we say that your process or the system have reached a condition of what we call equilibrium. That is the case, there won't be any transfer of material or energy in that particular system to or from the system. So the rate of mass transfer in here could be said to be directly proportional to the driving force. So the driving force, whenever this is present already, then we have departed, or the system is said to have departed from equilibrium condition. Now, to be able to evaluate the rate of mass transfer, so the driving force has to be accurately determined, and this is relying on the equilibria between phases. So the driving force depends on the type of unit operation. So it could be a pure mass transfer thing, or it could be a pure energy transfer thing, but commonly it's both mass and energy transfer that is occurring simultaneously. So we know that if mass transfer has to occur, there has to be differences in concentration. So there has to be differences in concentration or amount. And if energy has to be transferred, of course, we know that there has to be a temperature gradient. So without these driving forces, there won't be any departure from the condition of equilibria or equilibrium. Now, in nearly all situations, in unit operations, we are dealing with two phases. Even if we're talking about two solid phases, most of the time you're dealing with liquids and gases, liquids and liquids, and even solids and gases, or solids and liquids. So there is always this presence of two phases. Now, the controlling variables for equilibrium are the intensive properties. Again, the term intensive: temperature, pressure, and concentration. Okay, so we'll go back to our slide because it's not moving. The controlling variables for phase equilibrium, for the departure from phase equilibrium, is temperature, pressure, and concentration. Now, speaking of equilibria, we have data that tells us whenever there is equilibrium or there isn't any equilibrium at all between our phases, or in what particular concentration in the liquid and in the gas phase is equilibrium reached for a particular system that we have. So in this case, the equilibrium data can be read as shown on tables, or it could be shown in the form of equations, or it can be shown in terms of graphs. So I go first to tables. It should have been hyperlinked, but since this will not move, then I'll go to that particular representation on the table. So in terms of table class, it would be something like this. Equilibrium data in the case of the benzene toluene system can be presented in this form wherein you have temperature here in the first two columns, one in Kelvin, one in centigrade or Celsius. Then you have the corresponding vapor pressures of benzene and toluene and their corresponding mole fractions, and rather the corresponding mole fraction of benzene in the liquid phase, that's XA, and in the gas phase, that's YA. So the A that we're referring to in here is benzene because these last two columns is referring to benzene. So what is the purpose of this table? So from this table, we know that a particular temperature, let's say of 90 degrees Celsius, the vapor pressure of benzene in the benzene toluene system, meaning benzene and toluene is existing in that system, is 135.5 kilopascal, or it could be expressed also in millimeters of mercury. And that of toluene is 54. And in this particular temperature also, at 90, we know that the mole fraction of benzene in the liquid phase is 0.581, and in the gas phase is 0.777. So this is how we use this table. Now, although this table, if plotted, will not be really linear, this will really be in the form of a curve. When we are not provided with the curve, nor your Paris handbook does not show you the equilibrium curve between benzene and toluene as to finding the mole fraction of benzene or mole fraction in the gas or in the liquid phase, or finding the vapor pressure of benzene, then you can use interpolation for this one. But if you're going to really ask whether interpolation can be is applicable rather in this table, it's not, because we can only interpolate if the relationship between our data sets are linear. If they're not linear, then you cannot use interpolation. But as I've said, if there aren't any diagram that will give us the relationship that we want, something equivalent to this, then interpolation would do as an approximation. But oftentimes we have also diagrams. Okay? So that's in the form of tables. So equilibrium data can be taken from tables, as stated here, or can be in the form of equations. So in the form of equations, you have this one. So it could be in the form of Rayos Law. Rayos Law is only applicable to ideal systems. Systems wherein the components are said to be behaving more or less similarly with another, or their behavior is comparable with another. So if you have components A and B in that system, we say that system is ideal if A, in terms of characteristic of behavior, is the same as that of B. Then we say it's ideal. And Rayos Law is only applicable for such system. So what is Rayos Law? It gives you the relationship between the partial pressure of A in the gas phase and the mole fraction of A in the liquid phase. So if you notice in the table that was shown to you a while ago, there is vapor pressure, and there is mole fraction in the last column. So the mole fraction in the liquid phase in there can be associated to the partial pressure of benzene in the gas phase, because we know that in the case of benzene and toluene, we have two phases. We have the liquid phase and the gas phases. And in that liquid and in this liquid and gas phases, we have mole fractions of each of the components. So if we have a two-component system, and let's say component A in the liquid phase is 0.7, it follows that B is 0.3, because it has to be 100%, of course, in terms of the mole percentages. So in this case now, we don't find the partial pressure of A from a table, but rather based on the mole fraction that is given in the problem, we solve for it using Rayos Law. What is good about this particular Rayos Law is that if the problem already states the mole fraction of A in the gas phase, rather the mole fraction of A in the liquid phase, because this is XA, Y is for the gas, then we can solve for it, not that we're going to read it somewhere. So your vapor pressure of pure A is the vapor pressure that you're taking from the table. So inisyo si XA kag inisyo si PA is actually this one that was shown to you in the table a while ago. It could be read from the table. So mole fraction of A, this one. If this mole fraction of A, benzene, is multiplied to its vapor pressure here, 135.5, when the system is at a condition of 90 degrees Celsius, you will be able to determine the partial pressure of benzene where? In the gas phase. Having this vapor pressure and mole fraction of benzene data from the table. If this is not provided in the table, then the problem should provide it for you. Or if not all is provided to you, then you may take the missing information from this particular table. Okay, so it's this table together with the formula, or the formula together with what is provided in the problem. That way you can determine the required information or informations. So that's it. So this table can be used together with the formula by Rayos Law. Where was I? Okay, so that's for Rayos Law. The law holds only for ideal solutions as mentioned already. Do you follow? So our needed information can be taken from the table or can be solved using this particular formula, which can also use what is provided in the table. Of course, since that's for ideal solutions, then we should have an alternative if the solution or the system is not ideal. So Henry's law is one alternative equation. So in this law, Henry's law, you have partial pressure of A equal to the product of Henry's constant and the mole fraction of A in the liquid phase. So we just changed the vapor pressure in the Rayos law. This one is vapor pressure of A to the Henry's law constant if our system is not ideal. Now, the problem, class will let you know if the system is ideal. If the problem is silent, whether your system is ideal or not, don't assume that it's ideal. It should really be emphasized or specified in the problem if the system is ideal. If not, then use Henry's law. Now, in Henry's law, you have this constant H, and it could be taken from a table at the back of your reference books like John Copley's and McCabe. In one of the appendices there, you have the corresponding Henry's law constant at a given temperature. Okay, so you should find it there for a particular system because your table for system A and B will be different for a table for system C and D. So please later on check in your copies, soft copies or hard copies of your book if you can find at the end part these appendices that I am mentioning. It's also, of course, available in your handbook. I've checked in the handbook. We have a short example in the section on gas absorption and stripping on this particular Henry's law constant. And you can also try to find it in section 2, where all the information and data characteristic properties of substances and systems could be accessed. Okay? From this Henry's law class, if we will divide the entire equation by the total pressure of your system, partial pressure of A over the total pressure of the system will yield the mole fraction of A in the gas phase. And this H prime is actually the H divided by the total pressure of your system. That's the P sub T. Okay, the total pressure of your system. So H divided by P will be your H prime and XA is still XA. So your Henry's law can be written in this form or in this form. It's applicable for non-ideal systems. Okay, another equation that you will encounter in liquid-liquid extraction is K-factor distribution coefficient. It also depicts in the equation equilibrium relationship between the gas and the liquid phases in the form of this K constant or K-factor distribution coefficient. Now, in here, you could see, anyway, this will be discussed again. In here, you could see the ratio of the mole fractions in the vapor and the liquid phases at equilibrium. The I here refers to component I, generally any component I or any species I. So K sub I is equal to Y sub I over X sub I. It has an E, an added subscript E, because it's specified here that this should be the ratio of the mole fractions in the gas and liquid phases at equilibrium. Okay, now if for our system, Rayos Law applies and Dalton's law hold, meaning they are applicable, these laws are not violated. So number one, your system has to be an ideal system. This K-factor distribution coefficient could be also the ratio of the partial pressure of I over the total pressure of the system. That is if these two holds. Okay, if not, it's not anymore applicable. Okay, sorry. Now, another one on the distribution coefficient. If Rayos Law holds also, then the ratio of the K factors, the two K factors, let's say this is for your system, you have component I and you also have component J. Of course, your system should have more than one component. So if you have component I and component J in your system and you wish to get the ratio of their K-factor distribution coefficient, then that is equivalent as well to its relative volatility. That is if your system is ideal. So we can say that the relative volatility of an ideal system is equal to the ratio of the K-factor distribution coefficients of the components of your system. So K sub I over K sub J, or we say P sub I prime over P sub J prime. Or it could be the mole fraction of I in the vapor phase divided by the mole fraction of I in the liquid phase divided by the mole fraction of J, this time the other component in the gas phase, divided by the mole fraction of J in the liquid phase. So this is a continuation on the concept of the K-factor distribution coefficient. That is if Rayos Law holds in this case. So K-factors are strongly temperature dependent. So meaning if the system is subjected to a different temperature, it changes. But the relative values for K for two components change only moderately. So meaning even though generally K changes with temperature, but when we, let's say in this ratio here, when we get the ratio of the K factors of two components present in a system, when both are measured at the same changing temperatures, the deviation is just moderate. So hindi gid siya naglain if there were no changes in the temperature. So meaning you get this particular ratio at temperature, let's say 100 degrees Celsius, and you get this same ratio at 70 degrees Celsius, the variation will be just moderate. Again, if our system is ideal. Okay? So in the case of the application of this particular formula, starting with Rayos Law to Henry's Law, to this K-factor distribution coefficient, which I did not dwell so much because you will encounter them again in liquid-liquid extraction, you have the sample problems. And anyhow, you have the solutions under each. Okay? So for the first sample problem, let me try if this will project so it will be bigger, class. Let me know if you can see. Can you see? Is it project? Yes, okay. So wala lang siya gidyaga transition. So in this first sample problem, the partial pressure of CO2 in air is 1.333 times 10 raised to 4 Pascal. And the total pressure of your system, CO2 and air, is 1.1333 times 10 raised to 5 Pascal. The gas phase is in equilibrium with the water solution at 303 Kelvin. So what is the value of X sub A of CO2 in equilibrium in the solution? So you are to determine X sub A of CO2 in equilibrium with the solution. Now in here, you have to determine, or you have to use Henry's law because there was no mention that your CO2 air system is ideal. So in this case, you need the Henry's law constant. So you look for the Henry's law constant for CO2 at 303.2 Kelvin, either in your handbook. I leave that to you. You look for it in your handbook, section 2, or in the section on gas absorption and tripping. And you can look for it in your John Copley's or McCabe books. So you can find it also there. So you need the temperature, as I've mentioned a while ago. So it's stated here that you are to get the Henry's law constant at 303.2 Kelvin. If, since the problem here, class gives you 303 Kelvin, why use the H value, the Henry's constant, at 303.2 Kelvin? Because it's a very small deviation from 303. If you really wish to get the value at 303, you can interpolate. So you can interpolate between two temperatures where 303 is in between of. Okay, from that particular table. So from Appendix 8.3-18, page 988 of Gian Copley, so this is your Henry's law constant, having the set unit atmosphere per mole fraction. So we know from Henry's law that the partial pressure of CO2, in this case, A is the component of interest. So partial pressure of A, CO2, is equal to the product of its Henry's constant, of its Henry's law constant, and its mole fraction in the liquid phase. Okay, so what we do here is using the total pressure of the system, using the partial pressure, rather, it's given here partial pressure. The partial pressure of CO2, we convert it to atmosphere. The given in the problem is in Pascal, but your Henry's law constant is in atmosphere. So if there's a need for you to have it converted, then you use your Henry's law constant, and this is already your mole fraction. So that's a direct substitution on the problem, on the application of Henry's law to this particular problem. So this tells you that whenever the partial pressure of CO2 in CO2 air mixture is this value for a total pressure of this, then this will be your mole fraction of CO2. Mole fraction of CO2 where? In the liquid phase. Okay, because it's X. Compositions in the liquid phase is X. Composition in the gas phase is Y. So that's how we represent it in here. Okay, let me just go back here and then project that way. It will project properly. Just let me know if it will not project. Okay, second problem. Can you see it? Is it projecting?
Yes, miss.
Okay. So mabudlay na siya. Kaya every time I need a bigger slide, I need to go first to slide to the slide. Anyway, so at 303.2 Kelvin, the concentration of CO2 in water is given in mass. In mass ratio. I say mass ratio, class, it's not mole fraction, it's not mole ratio, because you could see here kilogram CO2 per kilogram water. So this is one challenge here, because now the problem does not give you something that you can directly substitute, because the concentration is in terms of mass ratio. Using Henry's law constant, what partial pressure of CO2 must be kept in the gas to keep the CO2 from vaporizing from the aqueous solution? It's exactly the same question as before, but with a different data set. So you have to do something on the data that is provided, but the equation that you will be utilizing is the same. So you need to convert first your mass ratio to mole ratio. So this is the given mass ratio in the problem. And using the molecular weights of these two. So in here, in here you have the molecular weight of CO2, and in here you have the molecular weight of water. So using the molecular weights of the two, you're able to convert from mass to mole ratio. From mole ratio, I know you know how to do it, then convert to mole fraction. So if you have 1 mole of water, you have this much of CO2. So your denominator will simply be 1 plus this, and your numerator will be this one. That way, you will have the mole fraction of CO2. So you could see here, total number of moles is just 1 mole water to this much of mole of CO2, taken from our mole ratio here, and we get XA with this value. Now then we go back to our formula for Henry's law. So we still use the same Henry's law constant because we have the same temperature here. We use the XA that we got to get the partial pressure of CO2. So the same formula was used in the first equation, only that this time you're given a different data set, and instead of determining the XA, you determine here the PA. So this should be, what's the significance of this? This tells you that this should be the minimum. This should be the minimum partial pressure of CO2 in your CO2 water system that will keep the CO2 dissolved in your CO2 water system. It's the same thing. I think it's the same principle that is being used in carbonated beverages. There is a certain degree of partial pressure that is kept on top of the solution of your syrup and CO2 and whatever components your carbonated beverages has on top of it. That way, your CO2 will not escape from the solution. So that is why we have it capped. So that is why may tansan sa babaw siyang soft drink bottle. That way, the CO2 will not escape. The partial pressure on top of the solution is kept constant. Otherwise, once it's decreased, the CO2 will escape. It's the same thing with this. Once the partial pressure on top of the solution of CO2 water decreases from 0.698, your CO2 will escape. It will not remain in your CO2 water solution. Do you follow? Do you have any question here? Okay, I still have another one here. So this time, I'll project. Just let me know if it's not projecting. So this time, it talks about relative volatility of benzene and toluene at 90 degrees Celsius and 100 degrees Celsius. So you are to get from table 7.1, the table that I have shown to you a while ago, the partial pressure of benzene and toluene at 90 degrees and 100 degrees Celsius. Okay, you are to get it, rather the vapor pressure, not the partial pressure, class. It's the vapor pressure of benzene and toluene at 90 degrees and 100 degrees. Let me go back to the table so you will not forget where you're going to get, how you're going to use it. So this is the table. So if you're going to get the vapor pressure, not the partial pressure, this will be the line that you're going to get it. This will be for benzene and this will be for toluene. So once you have that, you go back to the required information on the problem. Okay, you read it from there and you determine the, this is say here, and determine the relative volatility. So at 90, this would be your relative volatility, and at 100, this will be your relative volatility. Partial pressure of vapor pressure of benzene over vapor pressure of toluene. Vapor pressure of benzene over vapor pressure of toluene. That's how you make use of the table to get the relative volatility. So for 90, this is where you're going to read. For 100, this is where you're going to read. Okay? Any question? This is not partial pressure. This is vapor pressure. Any question, class? So none? Again, let me proceed. So for problem 4, you calculate the vapor and liquid compositions of benzene and toluene at 85 degrees Celsius. So using Dalton's law, this is Dalton's law, if you recall from your chemistry 1, partial pressure of A plus partial pressure of B is equal to the total pressure of your system. On the assumption that our system will have a total pressure equivalent to that of the atmosphere, for our system to be in equilibrium with the atmosphere, so it is equated to 101.325. However, using Rayos Law, this one is Rayos Law, benzene and toluene is an ideal system class. So Rayos Law is applicable. So we know from Rayos Law that partial pressure is equal to the product of the pure vapor pressure rather and the mole fraction in the liquid phase. So we replace P sub A, the partial pressure here, with this product of vapor pressure and mole fraction in the liquid phase for both components A and B. So we have it here. And we took these two values of vapor pressure from table 7.1 again, the table that I have shown to you a while ago. So in here, you'll be getting a relationship between mole fraction of A and that of B in this equation. But we know that since we have only a two-component system, the sum of XA and XB will be 1. So your XB here was replaced by 1 minus XA. So it tells you then that the mole fraction of, in this case, if this is benzene, the mole fraction of benzene in the liquid phase is 0.78. Knowing this, you can get also the mole fraction of benzene excuse me, in the gas phase. Using fundamental concept learned in Chem 1, mole fraction in the gas phase is equal to partial pressure over total pressure. So partial pressure is again vapor pressure times mole fraction in the liquid phase. So you use this value that you got here and divide the product of these two, P and X, by the total pressure. So now you have here the information between mole fraction of A in the liquid and in the gas phases. As to question what is the mole fraction of B in the liquid and in the gas phases, that's XB and YB respectively, you just subtract these two values from 1 because we only have a two-component system. And XA plus XB will always be 1, just like YA plus YB also being equal to 1. Okay? So these are applications so far of how we use equilibrium data in simple problems related to equilibria. Okay, so we're here. From this particular part of our slide, I jump to that part wherein I've shown to you tables and equations that will use equilibrium condition. And also graphs class. These graphs, if it's hyperlink only, this will not be a problem. For graphs class, this will be the graph. If you don't have the table, then you can have this graph. So this is a graph of SO2 water system. So you have here partial pressure of SO2 and mole fraction of SO2 in the liquid phase. This is gas liquid equilibrium data for SO2 water system at 20 degrees Celsius. You also have here, by the way, how do you use this one? So knowing the mole fraction, from here you go up and then read the partial pressure of SO2 in the gas phase. So mole fraction in the liquid phase related to partial pressure in the gas phase. Here you have for benzene and toluene again. Never mind this 45-degree line. This particular data is used in distillation. I'm just using it here for illustration purposes. So the curve that we're interested is in here, this one. So you have mole fraction of benzene in the liquid phase in the horizontal axis and mole fraction of benzene in the gas phase in the vertical axis. Okay? So relationship between XA and YA presented in the form of a graph that was also presented in here. Ari siya, oh. Na. Kung i-plot mo ning XA kag YA, amo ni siya klasang makita niyo dire. So an alternative of the one that is in the table. So that is what I mentioned a while ago, that whenever you're provided with a table, it's not correct to assume that the relationships there of the parameters are linear. So hindi siya linear. Kaya kung i-plot siya, amo ni siya ang shape. Now, in the case of benzene and toluene, again, benzene-toluene system, you can have this diagram. This is used actually also in distillation. You'll have more fraction of benzene here. So it's either this time, more fraction of benzene in the liquid phase or in the gas phase. So pwede ni siya ang horizontal axis mag-represent XA or YA. And in here, you have the temperature. So what you do, using the temperature, and using the appropriate curve, this is for the saturated liquid curve, and this is for the saturated vapor curve. What you have in between is the mixture of liquid and vapor. You'll be able to tell the XA and the YA. So let's say, for example, at 100 degrees Celsius, you want to know XA, then you have to stop on the saturated liquid curve. Then read XA here. If you want to know at 100 degrees Celsius what is the mole fraction of benzene, you go straight to the saturated vapor curve, adding vapor. This is liquid. And read here on the same axis, horizontal axis, the Y. So what's the equivalent of this? The equivalent of that is this one. Using the temperature, you have this too. So it's equivalent to this one. It's equivalent to this. Okay, this one is used in distillation, the same thing as this one. Okay, this one is used in gas absorption and stripping. So that's it. So your data can be presented in the form or the equilibrium relationship or relationships between your components in your system can be presented in the form of tables, equations, or graphs. Okay? For most operations, however, the pertinent equilibrium relationships are shown graphically. So knowing the nature of the data itself, that they are temperature sensitive, so it's really important that we refer to tables or graphs. More importantly, graphs. I'll go for graphs because it does not assume at any time that the relationships in your data sets are linear. So you go to graphs to express or to have an accurate representation of the behavior at equilibrium of your system's components. Okay? So for basis for phase equilibrium, we have the phase rule. What's the phase rule? I think this was discussed to you in one of your courses already. So in the phase rule, we have the number of the degrees of freedom equated to the number of components in the system minus the number of phases plus 2. This 2 is fixed. So this is how we determine whether our system, in terms of what is specified in the problem, can be solved. Kung anong ginhatag sa problem nga data, kag kung ano ang iya gina-require nga data, pwede balaayhan nga ang problem ma-solve or hindi ma-solve. So knowing whether the problem can be solved or not, that will be expressed, or that could be determined using the phase rule. So the degrees of freedom, otherwise known as the variance, needs the number of independent intensive variables. number of independent intensive variables. So this could be any of these three, temperature, pressure, and concentration, or a combination of these three that must be fixed to define the equilibrium state of the system. So for us to know whether our system will attain a certain degree of equilibrium, we need to determine this degree of freedom or variance. So if it's 2, we get 2 from this, 3. Or if it's 3, then we need all this. Or if it's just 1, then any of this as well. So it needs to, this number represents any or a combination of these intensive variables. That way our system we can define the system state of equilibrium, or nang kung sa pag-solve lang gidya, kung hindi kaya kinahanglan gidya nga ma-define kung mag-reach ang system natom equilibrium state, kung para mabalaan ta kung ma-solve bala ang problem or hindi. If a fewer than f variables are fixed or stated in the problem, kung kulang ang kinhatag sa problem nga data than the one state determined from the degrees of freedom, an infinite number of state fits the assumption. While if f is too many, the system is overspecified. So kung damo-damo naman siya sa gina-require sa degrees of freedom, the system is overspecified. Kung kulang, it's just like in algebra, number of equations is less than the number of unknowns. So you cannot determine correctly or properly, or we say it's underspecified, the required information in the problem. So that's the essence of this phase rule or degrees of freedom. You can read more on this in Jean Couplis and Mackay regarding the phase rule. For example, for a two-phase system, variance is equal to 2, which is also equal to the number of components for a two-phase system. So for example, if pressure is fixed, ginhatag na sa system ang pressure, the liquid phase concentration can be changed independently. Then the gas phase composition and temperature can be determined. In most cases, class, the problem would oftentimes not mention the pressure. And it's okay to assume that if it's not mentioned, it's okay to assume that it's at atmospheric pressure, because it's very seldom that our system is not operating under atmospheric pressure. Otherwise, if it's not, the problem would specify it. So if that is the case, you're already the system or the problem specified already the total pressure, then any of the concentrations can be given, just like what is stated here. So pwede katagaan liquid phase concentration, pangayuon niya naman ng isa. Or tagaan niya ka gas phase concentration, ng isa naman ang iya pangayuon. So isa lang i-specify niya, okay na dahil kay maka-vary na siya sang iya ipamangkuton sa problem. So this is in our case, most of the time, if not all the times here, we'll be dealing with a two-phase system. Kaya I don't also cover until multi-component system. So we only have two-phase system. So oftentimes your problem will be like this. You'll be given already the pressure and one of the concentrations in one of the phases, then the other one will be unknown. Okay? That's it. So we've covered already these equations and these sample problems. Now, in terms of equilibria class, we're about to finish. In terms of phase equilibria for different processes, so for gas-liquid equilibria, this is for systems, of course, that have gas and liquid as its phases. So this is in the case of gas absorption, desorption or stripping, and distillation. So in these 3 unit operation processes that we'll be discussing, we'll be using gas-liquid equilibrium tables or data. Now, in the case of liquid-liquid equilibria, that would be in the case of extraction or liquid-liquid extraction. In the case of liquid-solid equilibria, we have leaching. Okay, leaching, we leach out a component in our solid, or we take it out from the solid matrix using a liquid phase. So that's in the case of leaching, and that's it. So that's in terms of equilibrium or the concept of phase equilibria. Now, more on this, there are added informations that you can read, which I also took from, by the way, from John Kuplis and some resources in the internet, the one that I placed in your module 1. Okay? Another short, very short slide that I'm going to show to you is in the case of the multi-stage processes to to discuss in a very short and concise manner the concept of stage-wise operation. Okay, let me just change my screen. It would have been not difficult if my slides could be linked because there's no need for us to go to this one. So in the case of multi-stage processes class, I'm on the slide on multi-stage processes. They are also known as cascades. And these are systems which are consisting of interconnected stages or units. That's in the case of gas absorption and stripping. That's in the case of liquid-liquid extraction, of leaching, of distillation. Primarily, only 2 of the separation processes that I will be discussing in this course will not have multi-stage processes. So each of the stages, each of these stages will consider or will apply the concept of equilibria, because the phases are contacted in these particular stages and only leaves that particular stage when equilibrium is already reached. Okay? Or the maximum amount of mass was already transferred to a particular phase we call the solvent phase. Okay? Now, in the case of multi-stage processes, each individual unit in this cascade received 2 streams. So, from the adjacent units to it, the V phase or the gas phase and the L phase, which is the liquid phase, which are brought into intimate contact, as mentioned, and delivered afterwards to the same adjacent units. So units may be arranged either one above the other or adjacent or side by side another. Okay? This is a graphical representation from a cave, just in case you won't be able to see it, of a particular stage-wise process. Okay? So several stages in a column. So most of our columns in the industries isn't just a simple column. Inside that column are stages of contacting the streams that are being processed inside the equipment. So stage processes are this one. So I have mentioned already. Membrane separation processes are not stage processes or multi-stage processes. So in these stage processes, we'll have material balances. We'll do material balance. So it's either based on mole fraction or mass fraction depending on the type of operation. And we are most of the time using total material balance and component balance. Okay? We also do have energy balances, but this is in the case of adiabatic processes. And most of the problems that I have given and discussed so far are focused on material balances. But we don't limit the operation of these multi-stage systems to material balances only. Or we don't limit their analysis to material balances only. It will need as well energy balances. If energy balances are employed in unit operation processes, just like in thermodynamics, so enthalpy balances are the ones that are being used. Now, there are separation processes that we'll be discussing that will be using both graphical and analytical technique. So meaning we cannot purely solve something analytically. We'll have to refer to graphs, or we have to refer to, shall I say, illustrations that we ourselves made, okay, using the graphs or the tables. So this is in the case of 2 component systems only. Kung multi-components na siya, hindi na natin pag i-cover. The graphical methods that are being discussed specifically in John Puplis and McCabe are based on material balances and equilibrium relationships only, with complex methods requiring energy balances. Now, we will apply the concept of ideal contact stages here for these multi-stage processes. And in here, we look at ideal stage as a standard to which an actual stage is compared to. Later on in the processes that we will be discussing, you'll be determining the efficiency of the column or the yield. In that case, you will be needing to compare the actual separation in an ideal stage so that you will know how efficient is your column is, or how whether it's operating efficiently. So an ideal stage, in an ideal stage, the V phase leaving the stage is said to be in equilibrium with the L phase, leaving the same stage. So I have mentioned it a while ago. Hindi na iya maghalin ang phases na gipa-contact natin sa particular nga stage which we assume to be ideal, and that is it's behaving ideally if they have not reached a state of equilibrium. So the state of equilibrium is only, let me emphasize this, applicable to streams that have contacted already. Or shall I say streams that have left a particular stage. So ang streams nga i-contact pa lang, ang streams pa lang nga masulod pa lang sa ideal stage, hindi pa na sila in equilibrium with each other. After they have been contacted, that's the time that they leave the stage when they have reached already equilibrium. In designing a correction factor known as a stage efficiency or plate efficiency is used to relate the ideal stage to an actual stage, which I have also mentioned a while ago. Okay, so this is it, class. I have covered everything in Module 1 this afternoon. I have asked, let me stop sharing. Do you have any questions?